So we've been talking about market failures in the environmental realm, and one of the major reasons for market failures is often incomplete markets. And so in incomplete markets, it typically means there's some form of externality, a negative externality or a positive externality. So in a different video, I've handled a negative externality case, and I wanted to show you a positive externality case in this video, specifically a positive externality case that comes from a public goods problem. So let's end up flipping over to a shared screen here to work on that problem. So again, we're focusing here on market failures due to positive externalities in public goods. Now remember that a public good is a good that is sort of available to anyone but owned by no one. So anyone can benefit from the public good. There's no way to keep anyone from benefiting from the public good, and anyone who does benefit doesn't prevent anyone else from benefiting. So it is one of these funny things that is both non-rival and non-excludable, these public goods. And so we are going to focus on this so-called free rider problem that occurs in public goods, and we're going to model that on this kind of market-based supply and demand framework that we've been working with. So let's go ahead and draw that framework in here. So I am going to draw an axis here. There are axes here that, let's just say, I'll go give myself quite a bit of room on this axis and about at least 10 on this axis. I think that'll do. And again, this is the quantity of the good that is provided, and this is the price per unit quantity over here. Now, in the public goods here, we specifically for this simple model, we are going to assume that the marginal cost of producing the public good is, which by the way, I guess I should write, we're going to assume that the supply is equal to the marginal cost of producing the good, which in this case, I'm just going to say is equal to 1.4 times Q. And so for every unit of the good, you have a marginal cost of 1.4 times however many units are already being supplied there. So I'll just annotate this axis here so I can plot that out here so we see that this is 0, 2, 4, 6, 8, 10, and up here we've got 2, 4, 6, 8, 10, 12, and 13. So in this case, if I look at this 1.4 for the marginal cost, that tells me that for every 10 that I run, I rise 14. That's one way to view it. So I could say this is 14 over 10. Or I could say, you know, for every 5 I run, I rise 7. So I can go and plot that here, and I can say, well, 5, that's down here at this point, and 7 is right here at this point. So if I were to put a dot right there at 7 and 5, and if I were to connect those dots, then I could get the marginal cost. And I could actually, I might be able to get in, you know, if I run a full 10, I go up 14, which happens to be right up here. So what the heck, I can may as well put a dot right there. And I'll go ahead and connect the origin with those 3 dots. And there we go, that is my supply. And I might as well, I could even just move this over to be next to that line. All right, Now, in a public goods problem, so this is the supplier, so your public radio station or whoever, this is the one who's saying for every amount of quantity that they supply, then this tells them the marginal cost of the next unit that they could supply. And so in a public goods problem, you're going to have those that actually that they pay in to, they actually participate in the market. So those are the ones that actually have a demand curve. And so we're going to call those the members in this kind of public radio model. So we can say then that the demand curve is equal to the marginal benefit to the, and I'm going to call them members, so MB sub M, and I'm just going to make their curve 6 minus 0.6 Q. So if I go over here, I say, well, there's 6, and this 0.6, that means that for every run of 10, you fall 6. So 10 is down here, and 6 is this whole distance. So that means that I'm actually going to intersect the axis right here. So if I could draw a line that connects those two, then right there, that is my demand curve, which again is equal to the marginal benefit to just the members. These are the people who are paying for the good. And so because those members are paying in, then we end up getting a market equilibrium. And that market equilibrium is where these two things intersect. And so we can solve for that. So by solving for setting demand equal to supply is equivalent to saying that we're going to make 6 minus 0.6 Q equal to 1.4 Q. I can take the 0.6 from the left-hand side, add it to the left-hand side and the right-hand side to effectively move it to the right-hand side, and then I end up getting 6 is equal to 2Q, in which case then, and I guess I should make this QM for market, and then I can say that QM is equal to 6 divided by 2, or 3. And so this, if I drew this about right, then that tells me that, yeah, QM is about 3. And then, so what is the equilibrium price of the good? I just can't manage to draw a small m for some reason. All right, so the equilibrium price of that good, well, I can just take that QM and I can plug it into either one of the costs or the marginal benefit to the members, and I'll should get the same price out. So just as it's easier, I'm going to plug it into the cost curve. And so the PM is going to be equal to 1.4 times the QM, which is equal to 1.4 times 3, which is equal to, I have to make that a little times there to make it clear. So 1.4 times 3 is equal to 4.2. And so I can extend this over, and around 4.2, that's where I get the market price. Okay, so that is, if this was a normal market, this would just be supply and demand, fine. But this is a public good, which means there's going to be a set of freeloaders that are going to be able to experience benefit from this good without paying into it. So they have a marginal benefit curve, but their marginal benefit curve does not add to demand. And so the market doesn't properly price them in. And so you're going to end up getting an undersupply and an underprice of this particular good. So the freeloaders, so you can think of these are the people listening to public radio without donating, then those freeloaders, I can give them a marginal benefit curve, MB sub F for freeloader. And my, and I'll just say it's 4 minus 0.5 Q. So I can start at 4 over here, and this 0.5, which means for every time you run 1, or you run 2, and you fall 1, so that means that it's going to be here, 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 and then it's going to finally hit down here at 8. So I'll go ahead and draw a line that connects those. There we go. And so now we have, and I guess I should mark that, this is the marginal benefit for the freeloaders, this line right here. Okay, so what this is saying is that at the market equilibrium, the only people paying in to this market are the members. So there's just a set of people paying in, and they're the ones that are setting the allocation of this good to society. But there are other people in society that are receiving benefit that are not paying in, and we can see how much benefit that they're receiving. At the market equilibrium, we can see that they are actually receiving a bunch of benefit to the point where their marginal benefit is down here. It's not insignificant. So they, for the amount that is provided, for every new unit that would be provided to the market, they are experiencing a benefit for that new unit that's somewhere around, I don't know, 2.5 or so. We could solve for that point if we wanted to. So this is telling us that although the market has come to equilibrium where supply is equal to demand, if everyone was paying for the benefit that they received, then what would happen is that the producer could actually end up producing more. Like, in other words, the producer could raise the price, and the producer would still end up getting not just the QM that is already, but would still actually end up getting more as well. So at this level, the producer would get not only the quantity consumed by these consumers, but an additional quantity consumed by these consumers. And the producer could end up raising the price to help compensate for this, and you'd end up reaching a new equilibrium. And so we would like to know is, what is that new equilibrium? So if this marginal benefit was included in the demand, then the kind of ideal demand, so I could call this yeah, I guess I could call this the ideal demand, is going to be equal to the marginal benefit from the members plus the marginal benefit from the freeloaders. And so I can add those things together, 6 minus 0.6Q plus 4 minus 0.5Q. And that gives me 10 minus 1.1Q. And so I can plot that out, and maybe I can use gray for that. So this ideal demand I'm going to plot in gray. So I'll go up here to 10. And this 1.1 down here, that means that if you run 10, you'll drop 11. So I guess I could also say that that is equivalent to saying 5.5 over 5. So if you run 5, you'll drop 5.5. So if I run 5, well, 5 is here. So if I run 5, then I will drop 5.5, which is right down here. And so I can put a little point there. So I can say, well, I'll go down 5, and then in between here is around this point right here. And if I keep, if I try to keep going there, then, so I'm going to try my best to draw a straight line that intersects that point and then keeps on going down. And I'm going to actually stop there. All right, now why did I stop there? Because at the point where you supply 8 units of the good, then at that point, the marginal benefit from the freeloaders drops to 0. So if we look down here, the freeloaders, once there's 8 units of the good that's on the market, they don't care about any more of the good. it isn't worth anything extra for them. So they drop out of the market at that point. And all we have is our members, which are up here. So effectively, if I were to highlight this, maybe in gray, then the true idealized demand curve is the highlighted portion here. This portion plus, then it makes a little kink, and then it's that portion there, it's that highlighted portion there. All right, so if I look at that, then I can go and I can then calculate what the socially efficient equilibrium would be. And so that is going to be, I mean, the graph ends up doing some of the work for us, but let's actually go ahead and do the math. So if I set the ideal demand equal to supply, the ideal demand is 10 minus 1.1, and I'm going to use Q star because this is the socially efficient equilibrium. And then the supply is 1.4. And again, I'm going to use Q star. So then if I move the 1.1 Q star over, then I end up getting 10 is equal to 2.5 Q star. And then I divide both sides by 2.5, and I find that Q star is equal to 10 divided by 2.5, which is equal to 4. And so, not surprisingly, we find that 4, just based on the graph, I say not surprisingly because we drew it out with it there. So the graph is equal, where Q star is equal to 4. And then if we want to solve for P star, then we can just plug that in to the marginal cost curve. And that's 1.4 times 4, which is equal to 4 times 1.4, 5.6. And so this point over here is P star, which is about equal to 5.6. Okay, so the last thing that we need to solve for in order to best understand what's going on here is what is the, well, I mean, so there's a couple of different things that that we can handle here. Is basically what I'm interested in is what is the deadweight loss to society, given that we are undersupplying. And so what that looks like here, I'll just go back to black, is that at the market, we are supplying this QM that's way down here, right? But we ideally would supply this here. So what this dot that I just drew is, this is the marginal the marginal benefit that society experiences at the market equilibrium. And we can see that the marginal benefit that society experiences at the market equilibrium is far higher than the marginal cost. And so the marginal cost is down here. So that indicates that this whole region, this triangle here, this is lost net benefit. And so if we just solve for the area of this triangle, that tells us how much net benefit we are losing by those who are benefiting by not paying in. If the ones that are benefiting, the freeloaders, paid in, then the supplier could supply more, which would benefit both the freeloaders and the ones that are already paying in. And because there would be more quantity of the product that would be supplied. Granted, the price that would go up, but you'd end up getting more quantity out there, and the overall benefit would end up going up. So we're interested in calculating this triangle right here. And so we need to solve for this point up here. So we know the x coordinate of that point is QM. And then the y coordinate there is just going to be the ideal demand evaluated at QM, which is just equal to 10 minus 1.1 QM, which is equal to 10 minus 1.1 times Look over, what's QM? 3, which is just 10 minus 3.3. And just because I never do math in my head when I'm being recorded, then that ends up giving me 6.7. So that tells me that this price here is 6.7. And so we now, I think, know enough to calculate this deadweight loss. So I'll highlight the deadweight loss. Maybe I'll use a different color of gray, a paler shade of gray, perhaps. And that deadweight loss is that area right there. And so I know this distance and I know this height, and that's all I need to know. And so this distance here is just going to be, so I will write in here that this region here, the deadweight loss is equal to 1/2 times the base, which is this distance, which is just Q star minus QM, which Q star we see is equal to 4, and then QM, if we look up here, is equal to 3. So that's going to be 1/2 times 1 times, and then I'm interested in however high this is. Well, I know that this coordinate is 6.7, and my PM is 4.2. So I can write in 6.7 minus 4.2, and in that 6.7 minus 4.2 is 2.5. So the deadweight loss is just 1/2 times 2.5, which is 1.25. So that there is our deadweight loss. That's the area of that triangle there. And so if I wanted you to calculate the producer surplus and the consumer surplus, we could conceivably do that as well, right? So we would just end up saying, well, at the market equilibrium, the producer surplus is, well, we know that the price is down here. And so we can see that at the market equilibrium, the producer surplus is this triangle down here. And so I guess I can write that in, that this here is the producer surplus at the market equilibrium. And the triangle up here, no, I'm sorry, not triangle, the trapezoid up here. That there is the consumer surplus at the market equilibrium. And so what we can see here is that the consumers are actually winning out, but society would do better if we were operating at the socially efficient equilibrium. So we could calculate the producer surplus by calculating the height and width of this triangle. So the height of this triangle is PM, which is 4.2. The width of this triangle is QM, which is 3. So 4.2 times 3 is 12.6. Multiply that by 1/2, then you get 6.3. So that's equal to 6.3. And then the consumer surplus is this trapezoid up here. And so there's a trapezoid formula that says the area of a trapezoid is just 1/2 times the height of the trapezoid times the sum of the two bases. And so we just calculated that this base is got a height of 2.5. This base is 10 minus PM, so that's 10 minus 4.2. which if I do that here, 10 minus 4.2 is 5.8. So 5.8 plus 2.5 times the height of this trapezoid, which is QM, which is equal to 3, times 1/2 is equal to 12.45. And so right there, and then this is the deadweight loss down here. That's the other important quantity. And so if you add 12.45 plus 6.3, that gives you the current benefit to society at the market equilibrium. But if we would just, if the freeloaders would just pay for the benefit that they're getting from this public good, then we could produce more, even though the price would go up. That would end up increasing the producer surplus. That might end up decreasing the consumer surplus, but the overall benefit to society would end up increasing by 1.25. That's what that deadweight loss is capturing. So society overall would improve in the Cowder-Hicks sense. So we have a Cowder-Hicks equilibrium out here at Q star. All right, so that's most of the math that I would ask you to do here. I could do something else, and I could say, well, calculate the producer and consumer surplus at the socially efficient equilibrium. So this big triangle and this big triangle, I could have you do that. And that would be a legit thing to do. I'm not going to do that here because it's just going to clutter things up. And I hope it's kind of clear how things are working out here. Just for an additional interpretation, what we're seeing here is, and this is just a sort of a rough sketch, in terms of total benefit. So if we have our quantity supplied of the public good, and if we have our total benefit, then we basically know that the marginal cost is going to look something like this. So not the marginal cost, the total cost. So these are total cost and benefit. And so basically, we have the benefit to society is some curve that, say, looks like this. So this is the benefit to society. But when the demand curve only includes the members, and so in other words, the freeloaders do not pay for their benefit, then the apparent benefit to society, to the producer, is going to look like a rising curve that is much shallower. And so this here is the apparent benefit to society. And so what we can see here is that the apparent benefit to society may end up having the widest gap at some point. But if you include the total benefit to society, then you end up finding that the widest gap between benefit and costs actually happens to the right. And so the idea here is that if you only worried about the members, if all of society's benefit was just in the members, then we would end up producing a little bit less of the socially efficient equivalent or equilibrium. But because there are freeloaders out there that are benefiting as well, then our benefit curve is actually still accelerating faster than our cost curve is, which tells us that we should actually be making more. Because if we make more, we'll end up getting more benefits to society than the costs that we accumulate. And that will end up shifting the equilibrium over from QM to Q star. And that is sort of what we're trying to capture over here in this more precise way. All right, so that is our numerical example for the positive externality of public goods in this supply and demand framework.